So hello and welcome back. Today we're going to talk about operational amplifiers. An operational amplifier is a voltage-controlled voltage source that can be used to make various mathematical operations based upon how you connect resistors, inductors, and capacitors as an input, as a feedback value, and whether you're in the time or the frequency domain. So what we have here is an operational amplifier that is an inverting amplifier. I know it's an inverting amplifier because the voltage goes in through a resistor to the negative terminal, and I have a feedback resistor that connects the output to the negative terminal, and the positive terminal is tied to ground. You have to have power for an op amp to work. So here the positive power supply is 15 volts, the negative power supply is negative 15 volts. Note that an operational amplifier can never put out more voltage than the power supplies. So when it does, it's said to be in the nonlinear region or saturation. So what we're going to do here is we're going to analyze this op amp to find the output voltage and the gain. The gain is the ratio between the output V out and the input V in, which means that V out is equal to the gain times V in. When you have an op amp with negative feedback, there are two ideal assumptions that we make about the op amp. The first one is that there is infinite input impedance. And what that means is that the current into the negative terminal here and the current into the positive terminal here is equal to 0 amps. The second is that the voltage at the positive is equal to the voltage at the negative. So as long as you have a resistor, inductor, or capacitor that ties the output of the op amp to the negative terminal, that means you have negative feedback, then these two ideal assumptions hold. So now we're going to use KCL to solve for the gain and the output. So what we do here is we know that the positive terminal is 0 volts. That means the negative terminal is 0 volts. So when we sum the current into and out of the negative terminal, we know nothing goes into the op amp. So KCL at the negative terminal would be 0 minus V in over 2K plus 0 minus V out over 10K. And when we solve, we get that the gain is V out over V in equals negative 10K over 2K, or negative 5. So in general, for an inverting amplifier, the gain is negative RF, the feedback resistor, over RI, the input resistor, where RF is here and RI is here. So if Vn is equal to 3 volts, V out would be equal to negative 5 times 3, which is negative 15 volts. And thus is why it's called an inverting amplifier, because I send in a positive value and I get out a negative value. Or if Vn is equal to 2 volts, then V out is equal to negative 5 times 2, which is negative 10 volts. Or if I send in a negative value, such as Vn is equal to negative 1 volt, then V out is equal to negative 5 times negative 1, which equals 5 volts. So as you can see, it's an inverting amplifier because the sign flips, and it's an amplifier because it takes in a value and it sends out a smaller value. Although you can also make an inverting amplifier that attenuates or make the output smaller just by making the ratio RF over RI less than 1. So I want to show you one more example before we stop. So finally, if Vn is equal to negative 4 volts. So if Vn is equal to negative 4 volts, you would be most likely to say the output is negative 5 times negative 4, or 20 volts. No, this is not true. Because the op amp is in saturation, it could never output positive or negative 20 volts because the power supplies are at positive or negative 15 volts. So you would say it's in saturation and the output is 15 volts. Thanks for coming to learn about op amps, and I hope you'll come back again.